This class we can first see why we have to do algorithm analysis. So anyway, some explanation I have given earlier regarding this. Still we can see some more details. So why we have to go for analyzing the algorithm. So once again I can take one example. It's a very simple example, that is multiplying two integer values. Suppose you have two integers, let us say 12 and 25. You want to multiply these two integers. Normally what we do? So we write one number, then second number, then digit by digit we take and do the multiplication if the number is large. If it's a small multiplication, we can straight away do that. So here in the normal method, what we do is first we take 2 and multiply that. So this becomes 50 and this becomes 25 and totally 300. So this is what normally we do that. But this can be done in different ways. Another method, that is a French method, that is called ALRSC. Okay, there is a French method that is called the ALRSC. So here what we do is we write the numbers side by side, that is 25 and 12. One number is larger and one number is a smaller number. Suppose both the numbers are same, without loss of generality, you can take one as large, one as small. Okay, so you can take that way also. Here in this method, what we are doing is the larger number will be divided by 2 each time, and the smaller number will be multiplied by 2 in every iteration. So here what happens is 25 divided by 2, that is 12.5, but the 0.5 we won't take that, we take only the integral part. So we get 12 here, okay, and here if you multiply by 2, then you get 24. So once again we have to repeat that. One minute. So once again, if you do the same thing, here 12 divided by 2 is 6, here it is 48, 24 multiplied with 2, 48. So again we are doing that. So here it becomes 3 and here it is 96. Okay. Then if you do the division here, you get 1. Then here it will be 192, right? 192. And after that, what we get is 0. So we stop it. Okay. Once the 0 comes, we stop that. Okay. Now this is what we are doing. Now we have to find the answer. How we are getting is first we have to take the bigger number side. So in the bigger number side, we have to find odd values. So 25 is odd number, then 3 is odd number, 1 is odd number, right? So in the bigger number side, we have to take odd values, and once we select that, a corresponding value in the even number side, we have to take that. So here 12 is there, but this we won't take and this we won't take because these are all even, and 96 we take and 192 we take. So if you add that, you get 300. So this is another method. Okay. Then one more method I can say that this is based on Rig Veda. So there are 4 Vedas: Rig, Yajur, Sama and Atharvana. So Rig Veda, that it deals, this is not related to religion anyway. So Rig Veda, that is dealing with mathematical and scientific concepts. And there are a lot of sutras available for doing various mathematics, and that is what called Vedic mathematics. Okay, so from that I am taking one sutra. And name of the sutra, that is Nikila Navadas Karamam Dasadak. So Dasa means 10. Okay, so with respect to base of 10, I mean we can do the multiplication. Okay, let me explain how it is. Any other same number we can take that. One is 25, other one is 12, right? So we have to take the base that is near to 10 or a multiple of 10. Okay, in this case, if we take 10, the 10 is closer to 12. Okay, 10 is closer to 12, but it is little far away from 25. Therefore, what we can do is we can take the base as 20. So 20 is actually 10 into 2, right? 10 into 2. Okay, so if you take 20, 20 is near to 25 as well as near to 12. Okay, now what happens is with the 20 as a base, if you add 5, you get 25, right? With the 20, if you add 5, you get 25. And from 20, if you subtract 8, you get 12, right? Okay, now what we have to do is we have to split into 2 parts. The right hand side part, it's a small number. Anyway, we are taking the base and adding a subtracting, so it should be a small number only. So we can do the multiplication straight away without any difficulty, even if you take larger numbers. So anyway, it's a number is small number. Just to illustrate the method, I am doing it. So minus 8 minus 5 means minus 40, right? Minus 40, but only one digit available. So what we do is we put 0 bar, 4 bar. This bar denotes negative value. Okay, so 0 bar we have to take here, and when the 4 bar, one more digit there, totally it's minus 40. So denote minus 40, we put a bar over that, right? And left hand side, anyway, if you take this way, these two number, or you take this way. So this is 12 plus 5, right? 12 plus 5, 17. Or 25 minus 8, 17. Same value you get. Okay, you get the same value. So the value that you can write here, either you can take this way or this way. Both will give the same value, right? So 17 you get that. Okay, now the left hand side base we have taken is 20, that is 10 into 2, right? So the 2 can, first we can take 2, later on I can tell you that how quickly we can do that, right? So 2 we can multiply here. So if you multiply 2 here, then what you get? This is 34, right? And this is 0 bar 4 bar. Now this minus 4 can be taken out, taken to the left side. So that becomes 34 minus 4, right? So this is 0 bar. So 34 minus 4 is 30, right? And this is 0 bar. So already 2 is multiplied. Now 10 to be multiplied, right? So this becomes 300. This 0 bar. So now we can bring the 0 bar here. So this is 300 minus 0. So that is equal to 300. The same answer we get. So now several steps I put. Instead of that, what you can do is you can straight away multiply it by 20 here. Okay. So if you multiply 20, it will be 340 minus this 40. So that is equal to 300. So this also you can write. Okay. So why I have given three different methods? This is only for multiplying two integer values. Okay. That problem we know very well, but the same problem that is dealt in different methods. So the different methods actually gives different algorithms, right? So this is one algorithm because there is a step-by-step method of doing it. So this is one way of doing. So this gives an algorithm. This is giving another algorithm, and this gives another algorithm, something like that. Okay. So three different algorithms for the same problem. So obviously you may get the question which algorithm you have to consider. Okay, which algorithm you have to consider. So how you select that? So based on the efficiency of the algorithm. Okay, based on the efficiency in the sense that efficient in terms of time. If you are very particular about time, or if you are particular about the space, then the space should be considered, or both factors to be considered. So efficiency is determined based on the time and space. That's what we do the analysis. Okay. So in order to get the value, we do the analysis. So based on doing the analysis, when we have a multiple algorithms for the same problem, we are doing the analysis. Based on the analysis, we can find out which one will be the better. Okay. So the algorithm analysis, that is very, very important to find out the efficiency of the algorithm. Okay. This is only one small example to justify that why we have to go for the analysis. Okay, now once you analyze these factors, we should tell that, okay, how much time it will take. How you say that? How much time in the sense you cannot say something like a 14 second or 15 second or 2.5 millisecond. This way we cannot denote that. These are all practical time. So practical time we don't want. We want only the theoretical time. So theoretical time that should be based on the size of the input. Okay, that is based on the size of the input. So what do you mean by the size of the input? For example, if you are sorting n numbers, okay, the size of the input is n. In particular, if you say we want to sort 10 numbers, So because the 10 numbers will be given as the input, right? So size of the input is 10. So size on the based on but the size of the input that may vary. For example, I have developed a sorting algorithm. The sorting algorithm, initially I can give 10 inputs, then I can give 20 inputs, then I can give 100 inputs like that because algorithm is common. Only thing is input size that varies. Therefore, if you do the analysis should not be done for a particular example, okay, particular instant. We should not do that. We have to do based on the size of the because the size of the input that varies. Once we develop the algorithm for a problem, the size of the input that can vary. Several instances it may get right. So we do the analysis based on the size of the input. So when you do that, I mean we have to have some notations. Okay, we have to have some notations to define theoretically how much time it will take because there are a lot of theory behind it. I mean, whatever is required that we can take into account, right? And that notation is called asymptotic notation. So that notation is called asymptotic notation. So that is what the major topic we are going to discuss today. Asymptotic notation. So what we mean by this asymptotic? So actually, these time and space factors are being defined as a function. Okay. So if you say a function, the function can, if you plot the function, okay, the function can be represented as a curve. And if you draw a straight line, the asymptote of the curve, okay, if you say asymptote of the curve is something like, if you draw the line is infinite, okay, line segment is finite, right? So if you draw if you associate the asymptote of the function related to the line means, so where it is close to that line, I mean after far away, right? So that means here when we say the function in I mean related to the time or space, that means we consider what's when the size of the input is quite large, quite large. Okay, because as I mentioned earlier, if you have an algorithm for sorting the number of inputs that it can vary. That's the size of the input. Then what happens is what we have to see is we are not bothering about some small numbers, but we are bothering about when the large input size is been given. Okay, so we are taking the asymptotic value. We are taking the asymptotic value and the notation that is related to that we call as asymptotic notation. Okay, there are several notations available. We will see. The things which are needed for us for this course of study. Okay, so this class we focus mainly on this asymptotic notation. So first notation, now what we are considering is big O notation. It's O. Actually, we call it as big O. So because there is a small O notation also available. Okay, so we specifically mentioned that it's a big O. We have to put a capital O here. Okay, it's not capital O, it's a Greek letter, so it's called OH. Okay, big O notation. First, let me give the definition of this big O notation, then we can associate other things related to that. Actually, as I mentioned earlier, the things are being defined. That's the time or space that are all being defined in terms of the size of the input. So that means it's a function of the size of the input, function of the size of the input. So I think you might have studied functions, relations in your mathematics course, isn't it? Have you studied or not? Functions, relations. Did you study?
Yes, sir.
Yeah. So what's the difference between function and the relation? So you have studied, sets, function, relations, some, these are all very, preliminary things. Even you might have studied in your schools. What's the difference between function and relation? Because sometimes relation also will be defined in the form of a function, right? Because this is very important. Even when you take databases and all this and all, yeah, tell me.
So, yeah, In a relation, a single input can have multiple outputs, but in a
Okay.
function, a single input will have a single output.
Yes, yes, yes. Okay, actually the relation, actually what the thing is, the relation is between two sets of values. There is no specific thing, okay? Two sets of values. But a function, every output will be associated, I mean, with, I mean, well, every input will be associated with only one output, right? So this is what function. Okay, now we are talking, suppose I say that uh, f of n is equal to r of g of n. Okay, so this one, a function is been given in terms of a big O notation, big O of g of n. Okay, so if you want to say that here f and g are the two functions, we are taking that f and g are the two functions, and these two functions are defined from set of natural numbers to set of non-negative real numbers that we can say that are greater than or equal to 0. So non-negative real numbers. I will explain you later on why we take like that. Okay. F and G are the functions from set of natural numbers to the real numbers. If you say this f of n is equal to r of g of n, then there exists two constants. One is c belongs to r and n naught belongs to n, such that for all n greater than or equal to n naught, this f of n is less than or equal to constant multiple of g of n. Okay, if this is satisfied, then you can say this. So that's what we are saying. There are two functions f and g from set of natural numbers to non-negative real numbers. So that is all greater than or equal to 0. All values will be 0 or more. And in that case, if we say one function is we go of another function, then this property to be satisfied. Okay. Uh, Now, first of all, let us see, I mean, each and every term we used here. First of all, why the question is why we have taken the function from set of natural numbers to the non-negative real numbers. Why this n? Okay, why this n? So actually, when you say a time, okay, when you say a time, you may say that f of okay f of n. So this may be your size of the input, right? F of n. So this is a function in terms of the size of the input. Okay, so when you take the size of the input is always a natural number, right? You can say one input or two input. You cannot say that 1.5 input. You never say that. So size of the input is always a natural number, right? So therefore, the function is from okay a set of natural numbers to the non-negative real number because time if you say that there the real number possibility is there, but it cannot be negative. So either the time will be 0 or space will be 0, but or sometimes it may be a positive value, but it cannot be negative value. Okay, you can say that 1.5, 1.5, that is possible. Okay. So the what it is mapping to is the non-negative real numbers. So that's why we have taken the function f and g from set of natural numbers to non-negative real numbers. Okay. Then we say why we consider this f of n less than or equal to c into g of n. Okay, what it means. So, for example, if I draw a curve, okay, if I draw, I mean, if I take a x-axis and y-axis and draw that, maybe this axis related to n and this axis related to this f of n and c into g of n. Both we can consider two curves, one for this f of n, one for this c into g of n. We are trying to draw. So we assume that this is what our f of n. So once you draw the curve for the function, this is what we get. So this is only an example to illustrate this concept. That's all. We do not know what the function is. So some function is there. For the function, we can have a curve, right? So the curve is something like that. And we can assume that there is a another thing that is c into g of n. So that is the right hand side of this inequality. And if you take that, you can assume that that curve is something like that. Okay. And this is going like that and this is like that. Okay, now what we are saying is f of n less than or equal to gr when for all n greater or equal to n hat. Okay, for all n greater or equal to n. That's very important. So this is our axis related to n. This is our axis related to n. So, and there is a common point somewhere here. There both the values are seem to be same. So we can say that this is our n naught. This is our n naught. Okay. So what we say is for all values of n greater than that is after this, right? After this. So what happens before this n naught, we are not bothering about it. So sometimes the curve can go something like that, and maybe it may be lesser. Okay, we are not bothering about that. But after some time, after a particular value, whatever the value of n you are taking, that is what we are saying that for all n greater than or equal to n naught. Okay, that's why we say for all n greater than or equal to n naught. There, this f of n should be less than or equal to c into g of n. Okay, f of n should be less than or equal to c into g of n. Then we can say that big O. Okay, so what it actually denote that is whatever where the value of n even n tends to infinite, even n tends to infinite, this inequality holds good. And again, we are saying this notation is asymptotic notation. So asymptotic is something for a large. Okay, otherwise I can give another real life example. You assume that there is a ball. Okay, there is a ball, and there is a cat. And this is not looking like a cat. Okay, you can assume that this is a cat, and we assume that the cat will jump half the distance between the ball and the cat in every second. In every second. So in the first second, it may come somewhere here. Second again half, then another again half, then again half, something like that. So now what happens when the number of seconds goes off to infinite, but the cat never touches the ball. The cat never touches the ball, right? Because every time the cat will jump to half the distance. Cat will jump to half the distance. So even if n tends to infinite, the cat is not touching ball, but it is coming close to that. Okay, so this is what the asymptotic. What we mean is asymptotic. So in our, example, we assume that when this n goes to infinite, when n becomes large, so that time also this inequality hold good, and again we say that this is asymptotic notation. Okay, now the question is why this factor is for all n greater than or equal to n naught. Why we have to consider that? If we are not considering, what will happen? Okay, because this is very important. That's why I said that before n naught, we are not bothering about it. It may satisfy or may not satisfy. Does not matter. We are least further out. Maybe for 10 example, this condition may not hold good. Or 20 instance size, it may not be. Okay, doesn't matter. But for me, if I am able to find a n naught, the n naught may be 100 also or 1000, does not matter. But after that point, if the inequality hold good, I have to consider. Okay, this is what I want to say that. Once again, as you are the beginners, to make you to get clarity, I take one small example and illustrate. Okay, so that you get a clear idea. Okay, suppose your complexity is something like order of n by log n. Okay, n by log n. So when we say it's order of. Notation is big O, but when we say that, we say order of. ORDER, order of. Okay, so that's what we say. Suppose the complexity of our algorithm, complex in the sense that it's a time complexity or a space complexity. Okay, we can take time complexity. If it is n by log n. Okay, so if you take n by log n, you can because this n is a variable. N is the size of the input actually. So based on the size of the input only, we define the complexity. So that's what we are saying. Okay. So if you take that n by log n, n is the size of the input. So we do not know what the value of n is. So different possibilities we can try that. Suppose n is equal to 0. Okay, suppose n is equal to 0, we assume that, and that means there is no input, straight away the algorithm is running on something like that. But anyway, that is not have the meaning, just to illustrate I am saying that, okay. So suppose if you take n equal 0, substitute n equal to 0, then what do you get? So numerator will be 0 and denominator will be log 0, right? So that is equal to 0 by what's the value of log 0? Can anyone say?
Undefined, sir.
It's undefined. Why you say undefined?
Um, because log x to the base a, if it's equal to some value, it means a power that value must give us the log x value. So
Yeah.
here log 0 to the base 2 equal to, let's say, some value, then 2 power that value must give us 0, but 2 power any value won't give us 0. So
2 for an okay. Anyway, you have close to the answer, but formally you have to give more clarity. I think you have the understanding about. The concept. That's very good. I think you are clear, right? Okay. Okay, I can explain you why it's undefined is so you can take e power minus infinite. Anyway, the base is e. Base can be anything. The log 2 or log e or something log 10. Okay, so it may be natural logarithm or other logarithms. Does not matter. So whatever it may be, the base power minus infinite, if we take that, this can be said as 1 by e power infinite. So that is equal to 1 by infinite. 1 by infinite is equal to 0. So what do you have? Currently you have e power minus infinite equal to 0. If you take log on both sides, log to the base e I am taking, so that time this becomes minus infinite, right? So log base and this value is same, that goes up. Okay, the exponent value will come, right? So minus infinity, this is equal to log 0. So log 0 is minus infinite. So it's undefined. Okay, so this is the way we get. So whatever the base it is, log of 0 to any base, that is undefined. So that you have to remember. Okay, so this becomes 0 by undefined. So totally this becomes 0 by undefined. So this is the indeterminate value. Okay, 0 by minus infinity, that cannot be defined. So what we are saying is this complexity n by log n cannot be defined for n is equal to 0. It cannot be defined for n is equal to 0. Okay, now if you take n is equal to 1, what will happen? So n, then this n by log n becomes 1 by log 1. So that is 1 by what is log 1? What's the value of log 1?
0.
0. So log 1 to any base is again 0, right? So 1 by 0 is infinite. So once again, it cannot be defined for n is equal to 1. But from n is equal to 2 onwards, it's possible. Okay, if you take 2, what happens? 2 by log 2, maybe if log 2 to the base 2 means this is equal to 2, right? So this becomes 1 like that. Okay, so what we are saying now, in this case, if the complexity is something like n by log n, this cannot be defined for n is equal to 0 and n is equal to 1. But from n is equal to 2 onwards, we can do that. Okay, once again, remember the function is from set of natural numbers to the non-negative real numbers. So you have to take only the natural values for substituting the value of n. So you cannot take n is equal to 1.5. You cannot consider. Okay. Therefore, our value of n naught. So we have to find the value of n naught. So that n naught is 2. So now we are saying that for all values of n which is greater or equal to 2. So this 2 is our n naught, right? This 2 is our n naught. So for all values of n greater or equal to n naught, this complexity will be defined. So that's why this factor is very, very important. Maybe some cases before, and if you take a line that corresponding to the natural numbers, maybe if this is n naught, the values which are less than this n naught, it may or may not hold good. We are not bothered about that. But if you are able to find, the value is very important. If you are able to find the value of n naught, then from that n naught onwards, okay, n naught onwards, the inequality to be hold good. Then we can say that it is a order of or big O of that complexity. Okay, big O of that complexity. Okay, so I think the definition is clear. So if you have any other doubt on this definition, you can ask that. So this constant, you see this n naught is belonging to the natural number and the c is any real number, no problem. Constant can be, you can take some fraction also, okay. 1.5 or 2.5 or something like that, or 1.125 like that. So that can be a real number, does not matter. So some constant multiple of that g of n, that we have to get at. So any doubt you have on this? If you have a doubt, please Okay, so I can assume that you understood the concept. Okay, if you are not understanding the concept, then remaining portion will be tougher. So that's why I'm asking you to clarify before proceeding further. Okay, because after that, maybe after 10 or 12 classes, if I suddenly write some asymptotic value and that time you may, I mean, think that how it comes, right? So you should have a clear idea, and each and every class, whatever you studied, you should be thorough with that, so that next class, I mean, later on, if we deal with some concept, that will be easier and clear for you. Okay. Now, how we define? Because earlier the examples we have considered, for example, finding the maximum number, something like that. The time and space we have given something like 2n plus 1 or 2n plus 2, like that, or n plus 2, something like that. So that are all not been defined with this notation. That are all not been defined with the notation. Now to denote the complexity, we have a notation. One notation we have studied, that is a big O notation. Okay, so if those cases, how we represent that? For example, if your complexity is something like 4n plus 5. Okay, that how you get 4n plus 5, that you know that, because already we have discussed. Okay, in that finding the maximum, how we get that. Suppose you assume that you get this value. What is the big O notation of this one? So this big O notation of this one is equal to order of n. So generally, when you take this, these constant factors will not play anything, because this is a constant multiple of n. This is a constant multiple of n. Okay, and the constant will not be, because you can, if you are saying that f of n is less than or equal to c into g of n, this constant we are not taking. Rather, what we do, we say this f of n is equal to order of g of n. So the constant we are not considering for the order. So the constants are not important. And this is also plus 5, it's a constant. But when n grows, this fixed value is negligible, right? So this is not going to play anything. So we remove. So this is what the understanding many people will be having. And even many teachers, they teach like this. Okay. And the students also deal with that. The answer is correct only. Answer is correct only. But as a computer professional, you should not take that way. Okay. So maybe you can straight away write nothing wrong in that, and you even if you write like that, you get the mark. But you should know why it is. The reason is you have studied a definition, right? So we should see the definition. Already we have seen the definition for Bicon notation, whether that definition holds here or not. So what the definition that says that? It says that there exist two constants. One belongs to the real number, one belongs to the natural numbers. In that case, for all values of n greater or equal to n naught, one part is the left hand side part is less than or equal to the constant multiple of other part. Then only you can say, right? So all these things should be satisfied. Otherwise, you should not say. Okay, maybe for the writing purpose we can write. Sometimes it will work, sometimes it may not work. That's also very important. Okay, so mostly it will work. Okay, so if you write like that, we have to justify with the definition. That is very important. Okay, if I say this one, then what I want two constants. One is c, other one is n naught. So c belongs to the real number and n belongs to the n naught belongs to the natural number. So we have to find these two, right? So see, I can take something like 5. Okay, some there exists. Okay, it's not which there exists. At least one value should be there. I'm taking it as 5. Okay, c is equal to 5. If I take c equal to 5, according to this definition, okay, c into g of n. This is our f of n, and this is our g of n. Okay, this is our g of n, right? So what we can say? We can say 4n plus 5 is less than or equal to constant multiple of c into, okay, c into n. C is 5, so 5 into n. This inequality to be satisfied. This inequality is to be satisfied for all n greater equal to n naught. So you have to find the value of n naught now, right? If you are able to find the n naught, NAC already fixed. If you are able to find the n naught, for that, for all values of n greater equal to n naught, if this inequality hold good, then you can say that. Otherwise, you cannot say that. Okay. So we have to associate it with the definition. Okay. Now you see what value of n. Okay, I think okay, we can take 15. Okay, so better if we can take 50 because otherwise it may confuse. Okay, I can take 15, no problem. 15 also another constant because 5 anyway here 5 is coming. You may confuse with this 5 or that 5. Okay, so we can take 15. So 4n plus 15 that is less than or equal to 5n. So this inequality to be satisfied. So in this case, what value of n naught if we substitute so that this inequality will be hold good. For example, if you take n naught is equal to 15, okay, otherwise I can say n is equal to 15. Okay, here n. So if I substitute 15, what do we get? Here 4 into 15 plus another 15, that is less than or equal to 5 into 15, right? So here 4 15 plus 1 15, so that is 5 into 15. 5 into 15 less than or equal to 5 into 15. So the condition hold over. So if you put any value which is equal to 15 or more than 15, it will hold good. The inequality will be hold good. So we can say that this is our n naught. Okay, this is our n naught. So we say that the 4n plus 15 is less than or equal to c into. So c may be some value already we are taking 5 into n for all n greater or equal to 15. So we found n naught as well as c and the inequality, and hence we can say this. It is not otherwise because normally removing the constant and all, it's for I mean, kids, it's okay, but for computer students, that is not good. Okay, I think you got the idea. Maybe I can take one more example to justify this. Let us assume that I have another function, and that is 4n square plus 5n plus 12. So I assume that this function is there. Okay. So here what is the asymptotic value? So here anyway you remove the constants, finally the n has been taken, and here n square is there, n is there. So what is the asymptotic value? Whether I should take this or I should take this or I should take both, what will be asymptotic value? Okay, actually we have to take the maximum. So if you take n square is a maximum, and that will anyway some properties are there later on. So that it will be clear. For the time being, let us assume we take the maximum value. So compared to n and n square is larger, right? So we can take order of n square. So once again, if you write like that, you have to justify with the definition. So once again, I am taking c is equal to 5. Okay. Once again, I am taking c is equal to 5. If I take c equal to 5, this one, that is 4n square plus 5n plus 12 is less than or equal to 5 into n square. 5 into n square, right? So now I can take this term to the right hand side. Already n square at the right hand side, so this also n square term. So that can be taken to the right hand side. So it will be 5n plus 12, that is less than or equal to n square. That is less than or equal to n square. Now I can take the n term also to the right side. So 12 less than or equal to n square minus 5n. N square minus 5n, right? And this implies 12 less than or equal to, here n is common, n into n minus 5. Okay. So now what you have to do is substitute n is equal to 5. What happens? In this inequality, substitute n is equal to 5. Check whether inequality satisfies or not. Into 1 way, right? N equal 5 means this factor becomes 0, right? So 12 less than or equal to 0. Is it true? No, right? It is not true. Okay, now you put n is equal to 6 and see. Satisfying or not satisfying?
No, sir.
No. Okay, then n is equal to 7.
Yes, sir.
Yes. Okay, so yeah, so we can take n naught is equal to 7. So from 7 onwards, this inequality hold good. So we found C and n naught, and for all values of n greater or equal to 7, this inequality hold good. Okay, and again you can say that that is equal to r of n square. Okay, so that's why we are saying. Now the question is, I said we have to take the maximum. we have taken this factor but not this factor. Okay. Suppose you may make an argument that this also having the size of input. Why don't we take it as order of n? Okay. So we have to justify that this is not equal to order of n. Okay. Now we are saying that 4n square plus 5n plus 12 that is not equal to order of n. Not equal to order of n. Okay. So here what we can do is um, suppose we assume that suppose it is order of n. We assume that suppose it is order of n. So if it is order of n, then we can say that 4n square plus 5n plus 12 that is lesser or equal to some constant multiple of n. So the constant is c alone we can take. So this is counter argument. We assume that if it is order of n, otherwise we cannot write that. Okay, if it is order of n, then we can write this. Okay, now in this case the value of c will be more than 5, right? Value of c will be more than 5. Why? So anyway, I haven't put any value for c, but I have taken at a variable, it's that c, but I am saying that the c should be more than 5. Why? Because left hand side already 5 in the n is there. Here c in the n, but the c in the n is the larger quantity. So if I put 5 or something lesser, anyway left hand side will be larger, right? And already plus 12 is also there. So surely the c will be more than 5. So that is very clear. Okay, that we know. So we can say that we can keep this term 4n square. Then we can take the remaining term to the right hand side. So this becomes c minus 5 in the n, but c minus 5 is a positive quantity. Okay, c minus 5 in the n. C is anyway greater than 5, right? C minus 5 in the n minus 12. So this we get. Okay, now we have to see that whether we are able to find an n naught. Okay, and we have to say that we are unable to find a n naught. Okay, then only the thing, because c can be any value you can take which is more than 5 we can take. Anyway, that we can see later. But if we are able to find a n naught, then from that n naught onwards, if the inequality hold good, then we can say, otherwise we cannot. So we can take some value. Let us take n is equal to some k into c minus 5. We take like that. Okay, some k into c minus 5. So if we substitute this value, this is 4k square, left hand side. 4k square c minus 5 the whole square. And right hand side, what it is, you get k into c minus 5 the whole square minus 12, right? Minus 12. Okay, now what we say, you see, if you look at the left hand side and right hand side, what happens? Left hand side already k square is there. Here only k is there, but this term is common. C minus 5 the whole square, c minus 5 the whole square. Okay, but left hand side here k square, but we put a less than. This is less than this more, and moreover, we are subtracting 12, even lesser. But totally, if you take even lesser that. So this inequality cannot hold good to any value of n, right? Any value of k, not any value of n. N we substitute that any value of k you take, this inequality cannot hold good. Therefore, you cannot find the value of n naught to satisfy this inequality, and hence we cannot say this is order of n. So we are saying that it is not equal to order of n. Okay, so this much theory is behind that. But straight away, based on this equation, sometimes people will write. Okay, it's okay, but you should know that why we say like that. So for that, I have given the justification. Okay, fine. Now we can see some properties. Properties of big O notation. Properties of big O notation. The first property is if we take order of f of n, okay, one more thing. Yeah, otherwise I can come afterwards, no problem. Even next class also you can see, no problem. So if you have order of f of n and order of g of n, so if you add that, so this is equal to order of maximum of f of n comma g of n. Order of maximum of f of n comma g of n. So that means if you have two bigger notations, the final result will be the maximum of this one. How? If you say order of, okay, I can take left hand side. So left hand side is equal to order of f of n and order of g of n, right? So this I have. If you say order of f of n, that is less than or equal to some constant multiple, the constant I can take for C1, some constant multiple of f of n, and this one is some constant multiple of g of n. And we say that the maximum of these two will be taken. We do not know which is maximum, f of n is maximum or g of n is maximum, that we don't know. So without loss of generality, without loss of generality, already explained, you can take anyone as a maximum. So without loss of generality, we can assume that this f is less than or equal to g. So g is larger. Okay, without loss of generality, we can assume that g is larger. So if g is larger, then this inequality becomes less than or equal to C1 into f, C1 into g of n. Anyway, because we put less than or equal, right? G of n, f is less than or equal to g of n. So I can put with a larger value. C1 into g of n plus C2 into g of n. So that is equal to C1 plus C2 into g of n. So the C1 plus C2 is again a constant. So constant multiplied g of n. So that is equal to R of g of n. So what is R of g of n? Maximum of these two, right? Maximum of these two. So that's why we are saying that R of f of n plus R of g of n is equal to R of maximum of f of n comma g of n. This is one of the property. Okay, few more properties there that we can see in the next class. Before that, let me clarify this with one example. Suppose I take, okay, suppose I take the thing as, one more property is any function can be represented by its order. Okay, I can give you the justification later on. Okay, f of n. F of n is equal to order of f n. Why? It's very simple because we can say that f of n is less than or equal to 1 into f of n, right? So 1 is the constant. So we can say right like this. Any function can be written as order of itself. Okay, so now if you have 1 plus 2 plus 3 plus etc. plus n, so this I can write that order of, okay, order of maximum of, okay, according to this property. 1 minute. Yeah, so order of maximum of 1 comma 2 comma etc. comma n. Okay, so based on this property, I'm substituting this property, that is the order, because every value is order of itself, right? Every value is order of itself based on the, therefore this is something like plus 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 like that. Out of that I can take order of maximum. So what's the maximum out of these values? That is n, right? So this is order of n. Maximum of 1, 2, etc. up to n means n is the larger quantity. The larger quantity we are writing, that's order of n. Is it correct? It's not correct. It's not correct. It may look like we are applying the property. So that's why when you have the property, I mean, you have to be very careful there. Okay, this is not correct. What's the mistake we have done? You can associate it with the definition. Already we have seen the definition of a bigger notation. If you understand the definition, automatically you can say the answer. So where is the mistake? What mistake we have done here? Very big mistake we have done here. You see, nearly 1 hour I was teaching this notation with the different examples, and each and every symbols I have used, notations I have used. Okay, I explained it. Now you should answer it. What's a mistake? Kadir, do you have the answer?
I'm not sure, sir. I don't
Not
know.
sure. Okay, no problem. You see, the dimension itself, initially what I mentioned, the functions f and g are in terms of size of the input, right? This is from set of natural numbers to the non-negative real numbers. That means the functions are in terms of the size of the input. So is 1 is the size of the input? No, it's a constant. 2 is a constant. 3 is a constant. So you cannot take its order of 1, order of 2, something like that. Okay, you cannot take order of 1, order of 2. You cannot take that. Because when you can take is if it's a size function in terms of size of the input. Here, what is the size? N is the size. N is the variable. Okay, that's the size of the input. Therefore, these things are constant. We cannot take that. Therefore, this equation, what you have to do that? You have to simplify that. So that is equal to n into n plus 1 divided by 2. If you sum it, so in such a case, you have to sum it, right? So you will be getting n into n plus 1 divided by 2. So that is equal to n square by 2 plus n by 2. Now this 2 is not a factor, 1 by 2, that's a constant real number that you can remove. Out of these two, n and n square, the maximum you can take. Out of n and n square, maximum is n square. So that is equal to order of n square. Okay, so this is the correct answer. This is not the correct answer. This is the correct answer. So once you substitute the property, you have to be very careful. Okay. Now, anyway, time is up. We can stop the class.